So we have to get close, arbitrarily close. So when we talk about, getting really close in these output values, it's just arbitrarily close. Sequence convergence, we're only interested in what the nth term is doing. So follow me along here. Remember, a sequence is defined by its nth term. And for us, these are integer values, and an infinite sequence means n, integer-wise, can go all the way up to positive infinity. So for very, very, very large input values into our nth term, what are the outputs doing? Well, that leads us to the idea of a limit. So in this limit, as n gets really, really large of our nth term, what we're exploring is what are the final terms in the sequence doing. Are they jumping around all over the place? Are they oscillating back and forth between 2 or 3 or 4 or 10 different values? Or are they getting really, really close to a single value? If they're getting really, and again, that's arbitrary, close to L, then the sequence converges. So that takes all the guesswork out of convergence for a sequence. All we have to do is find the nth term, 9 times out of 10 it's given to us, and plug it inside this limit and see what we get. If we get infinity, well, infinity is not L. If we get does not exist, well, does not exist is not a real number value. And that's what divergence looks like. So we say if a sequence fails to converge to any finite number L, and this limit will express that for us, then the sequence diverges, or the sequence is divergent. So this is an important idea that we will carry on into series, so make sure this is in your notes with some highlights around it, because this is true for sequences, but we find out it's true for series as well. We do test, here we're doing the limit as n approaches infinity, on our sequences, and we'll find we do the same thing on our series, to test for convergence. If we cannot determine that our sequence or our series converge, then it must diverge, because there's only 2 choices. And if we can't confirm convergence, then in the absence of convergence, we have divergence. All right, so that's an important idea. For sequences, it's really straightforward. There is a close relationship between the idea of a sequence and the idea of a series, but convergence for these 2 things are completely different. All we're doing on sequences is we're determining how do the last few terms in this sequence behave. In other words, as n gets really, 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 really large, do the terms in this sequence get really, really, really close to a real number value? If they do, the sequence is convergent, and it converges specifically to the value of L. If they don't, for whatever reason, the sequence is divergent. End of story. So here's what convergence to the value of L would look like, again, if we were to plot these terms in the plane. If we said that the inputs were the integer values starting with n equal 1, and the outputs were the actual element values, the term values in a sub n, and if those, as n tends toward infinity, get really close to the value of L, then our sequence converges, and converges specifically to L. There are two different kind of sort of ideas here, and our elements continue to go. There is where we hover right above, we would have a lower bound of L. Here is where, over infinity, our sequence just bounces up up and down and up and down and up and down, above L and below L. But we can see that as n tends toward infinity, it does it in such a way that the term values get closer and closer and closer to L. And we're interested in what those terms are doing. If they're getting closer to L and sticking there, then we have convergence. So since we're going to be using this limit idea to test for sequence convergence, let's do a quick review of our limit theorems. And let's do them in the context of no longer functions, but of sequences, of nth terms. So we have a sub n and b sub n, and we are going to say up front that they are convergent sequences, and that k is some constant. Well, the review of the most common limits that we're going to be using are the limit of a constant is a constant. So that's still true. The limit of a constant times our sequence. The constant does pop out front, then we can take the limit of our sequence. And the constant k multiplied by, if this is a convergent sequence, k multiplied by L still gives us convergence. I don't care if k is positive, negative, super big, super small. We're still going to get a real number value out of that, and that's going to be convergence. It is true that just like functions, our limits break up over addition, subtraction, multiplication, and division. So all of that is still true. When we have this, now that we know L'Hopital's rule, if we need L'Hopital's rule, we can use it. Be very careful that x does not show up here. None of your sequences are going to be in terms of x, so be very careful. We treat the nth terms of sequences as if they were functions when it comes to limits, but we use sequence notation. So you're going to be taking the limit as n approaches infinity, not as x approaches infinity. Remember the Squeeze theorem for limits? It's true for sequences as well. If we have an nth term b sub n and we cannot figure out inside that limit what the terms are doing as n approaches infinity, then we could find a convergent sequence that is always smaller and another convergent sequence that is always bigger, as long as those smaller and bigger sequences converge to the same value. That's the secret to the Squeeze theorem. If I'm guaranteed this is the relationship between my sequences, and I'm guaranteed that both a sub n and c sub n converge to the same value, then the Squeeze theorem says it must be true that b sub n converges to the same value. So we could use the Squeeze theorem in this context as well if we needed to. Now let's talk about how a sub n looks. Sometimes, depending on the makeup of a sub n, we can call it a certain type of sequence. If a sub n is some real number r is some real number value. It doesn't just have to be an integer. If a sub n is of the form some real number r raised to the power of n, then this is a geometric sequence. And we don't even really have to put it inside the limit. By inspection, all we have to do is look at the value of r. If the absolute value of r is less than 1, which implies if r has real number values between -1 and 1, then we are guaranteed that a sequence of that form converges. Then a sub n converges. And since we're not going to put this inside of a limit and run an actual test, the sequence divergence test, when we encounter an nth term that looks like that, we have to identify it as a geometric sequence. And then we have to identify whether r, the absolute value of r, is less than 1. So a certain type of a sequence could help us as well. So number 1 says if a sequence behaves like an exponential function, we're guaranteed that the sequence will converge when the base of that exponential function, the base is r, lies between -1 and 1. And this is known as a geometric sequence. So we'll have to identify it as geometric. We'll have to show the AP reader. Let's say we had a sub n equals 1/2 to the n. Well, that's geometric. That's a real number raised to a power of n. We would have to show the AP reader that we recognize that's a true statement. And so we would say a sub n converges. It is a geometric sequence where r, the absolute value of r, is less than 1. And that's all we would have to do to prove our work. So make sure that's in your notes and you can use that on homework. The second thing here says if we run the limit of an nth term of a sequence and we don't care if it's positive or negative. If a sub n is -1 to the n times 1/2 to the n, then I don't care what the actual sign, SIGN, is on each particular element. If we were to generate this, starting at n equal 1, we would have -1/2, then we would have +1/4, then we would have -1/8. And what number 2 says here is I don't care what's happening. Forget the part that talks about whether the terms are positive and negative. And sorry, that shouldn't be there. Just worry about what the positive part of it is doing. If the positive part of it is going to 0, then that is a good result. L can be 0. So this sequence converges. And you've done the work to prove that it does. So number 2 follows from the Squeeze Theorem for sequence convergence. If a sequence converges to 0, then a negative sign in front of it will not factor into the convergence result. So this part is important. We have to converge to 0. Let's work some examples. Does the sequence, the natural log of n over e to the n, converge? And if it does, to what number does it converge? Well, the first thing we're going to look for now is it geometric? Do I have some real number value raised to a power of n and nothing else? Well, I do in the denominator, but I don't in the numerator. So this is not geometric. So this is one where I will actually have to run the test as n approaches infinity on the nth term, and I'm looking to see if that equals a real number value. So now let's just fall back, just like we did when everything was in terms of x. We're going to treat it exactly the same way, only now we're in terms of n. And if I was to plug in huge, I would get huge over huge. This is infinity over infinity. And this is what I was saying before. I can use L'Hopital's even in this context. So this cleans up to the limit as n approaches infinity, 1 over n times e to the n, that's 0. So this sequence, a sub n equals the natural log of n over e to the n, converges. So I have some more examples. We'll work those in a next video, so look for the next video.